Hello, my name is Caitlin Bache. I'm an assistant editor at ASHRAE Journal. Thank you for joining us for today's webinar, part of the ASHRAE Journal Supplier Webinar Series. The series provides information to high-performing buildings readers and to others about products and technology of interest to industry professionals. ASHRAE does not review supplier webinar presentations. The following presentation has been prepared by Mitsubishi Electric Trane HVAC. The subject is Making Sustainable Attainable, using VRF technology to achieve ambitious energy goals in mixed-use applications. Today's speakers are Kimberly Llewellyn, Jamie Armstrong, and Matt Dunn. Kimberly specializes in the advancement of high-performing building practices for low-carbon impact projects, including passive house, net zero energy, deep energy retrofits, with a particular focus on multifamily buildings. She is the Emerging Market Senior Product Manager. Jamie is the Commercial Regional Sales Manager for Mitsubishi Electric Trane HVAC US, focusing on the South Texas and New Mexico areas. He has 10 years of experience on the HVAC sales side of the business, in addition to 10 years as a professional engineer designing HVAC systems for large-scale commercial applications. Matt has over 13 years of experience in the construction industry with a focus in MEP systems. As an MEP coordinator, Matt is responsible for the interaction and coordination of all mechanical, electrical, and plumbing trades. Matt is currently the MEP coordinator for a new personnel center at Texas's Randolph Air Force Base. Kimberly, the microphone is all yours.
Thanks, Caitlin. I want to thank everyone for joining us today. Our team is honored to have the opportunity to share some information about this exceptional project with you. We know there's a lot of interest in electrification, decarbonization, and this project is really a testament to how to get her done, even here in the heart of Texas. We made it happen, and so we want to share some of that with you, what our playbook was. Let's go ahead and get moving on these slides. Okay. So just to review our learning objectives, we hope you're going to benefit from some description of the project goals and the ambitious sustainability goals, which we'll enumerate. We'll also be reviewing VRF technology basics. Jamie Armstrong will be covering that. And Matt Dunn's going to dive into how the specific VRF ground source systems, the high efficiency ventilation systems, and some of the other sustainable features really supported this project's sustainability goals. So I think that it's important to recognize that exceptional projects really start with exceptional people. So it's important to understand Create Human, the owners of this building. 6 years ago, they rebranded their company from San Antonio Credit Union to Create Human, the current name. And they did this in order to more clearly communicate what the core values of the company were. Create Human as a company is completely dedicated to improving the lives of their members. So it's a membership credit union. And they do this by helping their members create financial slack with the intention of reducing financial stress in their members' lives. And so you might be asking, okay, what does this have to do with new headquarters buildings? And I'll get to explicitly drawing that line in just a few minutes. The history is a fairly long one. So the credit union was formed in 1935 during the Great Depression, and they were one of the few credit unions that successfully navigated World War II and has continued to steadily grow their membership and their product lines over the last 80 years, 90 years almost now, to 235,000 members, serving 43 states. So they've steadily grown, but grown in a responsible way so that their reach doesn't outstretch their ability to very effectively serve that membership. So the credit union had been operating out of 2 buildings in Northwest San Antonio that had approximately a total square footage of 160,000 square feet. The new building that they moved into was 200,000 square feet, just as a point of reference. But the main building, which is located on Vance Jackson Boulevard, is a 9-story, 1976 built glass sort of hybrid curtain wall construction, and was very over time, over the decades, had become increasingly an energy hog, so that its annual electrical costs by the end of its useful lifetime were averaging $500,000. So a huge cost of operation. So not only were the operations being compromised by having to maintain 2 buildings that weren't functionally serving the credit union, but financially it was not really fiscally it was not responsible use of the membership's money, because that is how credit unions work. That is not for profit, but for the in order to support the membership. This is $500,000 a year in operations was not really fiscally responsible use of the membership's money. So all of this really was what led the ownership to rethink the buildings that they were operating out of. And when they outgrew physically these spaces, they started with a clean canvas. And with the credit union's core values at the heart of that vision, they imagined creating a space that would serve its employees and the community on a higher level. So at a glance at the new building, we've got a 12-story, over 200,000 square foot Class A office space. The occupancy is scheduled at about 1,200 employees, various meeting rooms. It's a building that, when you walk into it, people often are saying, like, I want to work here, because it feels great. So there are a lot of functional spaces. There's green inside. There are elements of local artists that have contributed, and so not only is it sustainable, but it's also pleasing to be inside this space. So a little bit about the team that was key to the creation of this. I've mentioned the credit union and their leadership, led by the CEO, Steve Hennigan, and then his team that supports him at Credit Union. That's where really the vision started for creating this kind of space that was fiscally responsible, that was an asset to the community, that was going to maintain its value over decades. Because you should point out that the credit union had occupied their former headquarter buildings for almost 50 years. And the intention here is that they occupy this building at least that long and maybe longer. So when you have that kind of long-term perspective on the building that you're designing and actualizing, the goals suddenly shift. And we think less about upfront costs and more about the cost of operation over a decade, 2 decades, 3 decades, and beyond. So that's where that started with the ownership. And then they quickly found a perfect partner in Silver Ventures. Silver Ventures had developed a historical property at Pearl Brewery, right at the head of the River Walk in downtown San Antonio. And, you know, in honor of the vernacular and those existing industrial buildings on that campus, they had done an amazing job to create a space that visually was amazing and also was an asset to the community in that it provides a lot of open spaces, parking, restaurants, and the like. So joining forces was really key in the success also of this property, of this project. The general contractor, Joeris General Contractors, whom Matt Dunn works for, and he'll be talking to us more later on in this presentation, were also an incredible asset to the team. Would not have happened. None of this would have happened without them. The dedication to the owner's vision, and then them bringing their own dedication of work quality and attention to detail, and really just the desire to do better. So they've been absolutely amazing and key. The architects, Don B. McDonald and Kirksey Architects, have, just looking at the building, you can see what they've brought to the project. The MEP design engineer was Glumac, Tetra Tech company. They were in constant communication and collaboration with our team here at Mitsubishi and with Matt Dunn's team at Joeris to make this a reality. And we're, obviously the manufacturer. So these were the key players of the project, but it was not that you have a good lineup. That's not the key of making a project successful. What really made the project successful was that, again, ownership from the starting gate made it very clear that there was an expectation that the entire project team would be in good communication, constant collaboration, and they established an expectation for mutual support. So there was no real top dog. It was more of a how can we serve each other to serve the overall arching goals of the project. And that's sort of hard to maybe describe in a webinar like that, the impact that has upon the overall outcome. But that really is what I think was the primary difference in this project compared to other large projects that I've been a part of. So having a little navigation issues here. So just to review on a high level some of the goals that were set by the project, and we'll review those high level here, and then Matt will get into the weeds later in this presentation. So the building goals, they were ambitious, but they were attainable. And the main goal was the ownership wanted to create a space that promoted both the employees and the community's wellness. So for the employees, indoor air quality was clearly important. We've got on this project primarily compact ducted systems. You can see one of those recessed here above the ceiling plane. They're outfitted with filters, and the fans are set for a minimum airflow, continuous airflow, which means that the systems are constantly filtering air. Additionally, there are high efficiency Swagon ERVs on the roof, and those are providing fresh air and also continuously exhausting air from inside the spaces. From a from a community standpoint, you could argue that promoting a sustainable operations is a benefit to the community, and the ground source VRF systems were key to lowering the overall electrical loads of the system. I'll talk about the resiliency perspective of that, I think, on the next slide. But in addition to the energy reduction and that benefit to the community, there are also spaces available to the community for use. So it was not like, let's create this amazing sustainable fortress that community can look at and admire from without, but there's actually an invitation to come into the building and to use the space and to use the courtyard on the ground level of this building, which is very much in alignment with that Pearl campus that's adjacent, Pearl Brewery campus that's adjacent to the Credit Human headquarters. Let's make sure I haven't skipped anything. So the ultimate original target in terms of utility cost reduction was to reduce the utility cost by 96% on a square footage basis compared to the building use of those other two buildings I described. As of today, the owners have reduced the utility cost by 100%. So for the first 7 months, 8 months, we were at something like 90%, and that gap has slowly been closing as the building systems have been tweaked for operation and streamlined schedules, and so they were happy to report that the goal has been attained. Of course, that's always moving and changing, but owing in part to the building automation system, which Matt will talk about later, we've been able to really dial in on the energy using systems and improve operations and those costs. So additionally, water usage is something that we don't talk about as often as we talk about energy usage as a key sustainability point. However, oftentimes water use is a higher expense than energy use, and we don't really think about that. So the water catchment system, which includes over 150,000 gallons of capacity in storage tanks, is a key part of the sustainability features and designs of this project as well. So starting from the ground up, though, on some of the key sustainability features of the building, we've got 152 geothermal wells. They're approximately 300 feet deep. From a resiliency standpoint, this is really key. For those of you who already designed ground source systems, I don't have to tell you why. These systems are much more commonly in use in very cold climates because we have a stable source heat exchange in the ground. The ground temperature is much more stable than air temperature, and for this reason, it is easier to maintain high COPs as you're delivering, in particular, heat to a larger building. So upfront costs are certainly higher for a well field, but again, when you're looking at longer ROIs being acceptable, it absolutely makes sense. I don't think I've mentioned yet that the target or design return on investment for this project was 12 to 13 years. At this rate, it's looking like it might, in actuality, be shorter than that. So we've got 152 geothermal wells. Then let's talk about the building envelope for a minute. You'll notice in looking at the building that, first of all, it's not all glass and steel. So that's one first huge asset. So there are actually walls in this building. Behind that beautiful brick masonry, there's a fluid applied air barrier and then continuous insulation. So those window frames are also thermally broken. So you've got both amazing air control layers and also thermal control layers on the building envelope, which goes a long way to reducing both heating and cooling loads of the building. And that's really where you have to start. So, to build an all glass and steel building, a building envelope that is not optimized for lowering the loads and then trying to make up for that with high efficiency mechanical systems and or PV, I mean, you can do it, but it's not really the most efficient way or the best use of resources to do it. So it always starts with the building envelope. That fluid applied air barrier, I don't know if Matt's going to get to talking about it at all. It's just one of the things I'm most impressed with about the Joeris team. The level of building tightness that they hit was close to Passive House. And if you go to the 1703 Broadway website, you'll find some pictures about how they went about testing every brick tie on that facade. And I don't know how many thousands of them that there were, but that is how they achieved that incredible air infiltration value. Additionally, we've got, I mentioned high efficiency ERV and ventilation systems. There is also a really advanced LED lighting and advanced plug load controls. So the control system, I think Matt might talk about, run under the flooring so that they've got a grid of which can be monitor the zones of electrical use for each of the zones on each of the floors, which allows them to optimize the energy use of those systems as well. So in terms of resiliency, resiliency is like a new buzzword, and we talk about it a lot, so we want to be clear as to what that means to us. So if you have a building that's resilient, I think of it being resilient to extreme climate conditions. And so an example of how well this building performed in our snowpocalypse was 2 years ago here in Central Texas, where we hit single-digit dry bulb temperatures and, had our grid went down for I don't know, 10 days. It was an extreme situation statewide. Many people suffered. Grids being down caused innumerable building damage, loss of life, et cetera. So this building and its ground source systems were able to ride out that event, maintaining a comfortable indoor air temperature, by nature of the ground source systems themselves, and to maintain those temperatures, comfortable interior temperatures, even when the exterior temperatures were extreme. So had those systems not been in place, and had the electricity, stayed on or not stayed on, not been able to maintain above freezing temperatures, the loss of the financial cost due to that kind of event never gets factored into our typical ROIs. And so that's something we have to change, in our design phase, in our pitches, is to have some sort of contingency calculation that has some consideration of, well, what's the possible cost of not being able to weather this kind of extreme event? What would the cost be if we had pipes burst, or if our systems did go down, or if nobody could come into work because the building wasn't warm enough, or. And so that's that's something else I think we all need to work on. So by offering, an all-electric ground source VRF system, the credit union has really stayed in alignment with its core values, lowering overall cost to its membership, providing a healthy, comfortable, and space that can be maintained at a responsible operational cost. So I'm going to pass this over now to Jamie, who's going to talk to you about VRF systems more generally, how they operate. Jamie, over to you.
Well, thanks, Kimberly. My name is Jamie Armstrong. I'm the regional sales manager for Mitsubishi Electric here in the area where this credit union building is installed. And I'm going to be just kind of going over some of the VRF basics. So now that we're all kind of on the same page, the VRF stands for Variable Refrigerant Flow technology and its operation and how it can be applied. So we'll get past, there we go. So VRF systems consist of an outdoor unit connected to a network of indoor units, which could be either ducted or ductless. VRF systems heat and cool zones by moving refrigerant through small diameter piping rather than traditional VAV where you're moving large volumes of air in larger ductwork, we're moving refrigerant through small ductwork, through small piping, During the colder months, these systems draw heat from the refrigerant in heating mode, and then in the hot months, these systems reject heat into the refrigerant when it's in cooling mode. So the graphic here depicts an air source system, which is a similar visual to a water source, which we use at credit union. So in contrast to VRF operation, conventional HVAC systems typically take a more centralized approach where ductwork is connected to a centrally located air handler, and there's large ductwork running out to different spaces. Some of the key issues with this is the more ductwork you have, the more potential for air leakage, which of course is directly related to your efficiency and your comfort within your space. When there is some sort of issue in the system, the extra ductwork can make it more difficult for contractors to find that leak and pinpoint the problem. So as we'll see in the next slide, the conventional method of the on or off operation, meaning that when the set point is reached, conventional systems turn off until a temperature threshold is met, which is extremely inefficient. So this slide here is showing the difference between a traditional stage compressor and an inverter compressor, which is what is on all VRF systems. So VRF systems use the inverter-driven compressor, which modulates the energy usage instead of constantly starting and stopping like traditional stage systems. Operating this way allows the system to keep up with the high energy demands of the mixed-use buildings while also maintaining the energy-efficient use of the compressors and also maintaining just a more constant space temperature rather than kind of creeping up. It feels like it's a little warmer, and then it turns on, and then it gets kind of cool. It's rather than the constant cycling, having the compressors be active all the time helps minimize the deviance from the space set point. And the system uses the precise amount of energy required to meet each zone set point. So this translates to efficiency and operational cost savings, as well as less temperature swings with increased level of comfort for the individuals in the space. VRF technology allows for indoor air temperature to be customized by zone. What most spaces that are in larger areas that may be served by rooftop, they could have one rooftop serving 6 or 7 spaces where one person is in control of the set point of that. So that's the huge advantage to VRF is you have the option for better zoning, and you can also do simultaneous cooling and heating, which we refer to that as heat recovery. Everyone always, in different spaces that are even sometimes next to each other, prefer different set points. The zoning also allows for temperatures of different spaces within a building that's entirely in one mode to be set a couple of degrees higher or lower to match the comfort level of the people in the space. In crowded spaces, for instance, where more body heat is being emitted, occupants may appreciate the air to be slightly cooler than in a more open area with fewer people. This is particularly beneficial for mixed-use applications where one building can serve multiple purposes. With so many spaces with unique functions and occupancies, having the ability to customize conditioning for each individual zone can make all the difference. So this is a slide showing one of our types of equipment, which is the heat pump. So in single zone applications and in moderate climates, the HVAC contractors will sometimes choose heat pumps. Heat pumps are an effective way when all the building zones can be in the same mode at the same time, so either heating or cooling. You can still have the individual set points on the indoor units, but the mode is the same. Either they're all in heating or they're all in cooling. And alternately, we can also provide simultaneous heating and cooling in multiple zones by cycling the refrigerant between an outdoor unit and indoor units, which is called heat recovery. The system can be flexible to zones that are occupied versus those not in use, and the heat recovery systems are what's specified for most mixed-use buildings, including the credit union building that we've been talking about. Depending on the location of your building, your efficiency goals, or existing equipment, there's two options. You got air-cooled or a water-cooled or water source system, which is what we've got at Credit Human. The condenser on the right is the air-cooled version. It could be either mounted outdoors, or we have other instances where the air-cooled condensers are even mounted indoors. And then the one on the left there is the water source condenser that those can be stacked, and that's what we've utilized for both the comfort cooling and also the outdoor air processing for the entire Credit Human building. So an air source system draws heat from the outdoor to provide heating, and in cooling mode, the system rejects heat to the outdoor air. Water source systems operate similarly, but they draw heat from a nearby water source during heating and reject heat to the water source during cooling. The water source could be a tower or geothermal, like we have at Credit Human. We actually have both. There's two towers on the west side of the building, and there's also the geothermal loops that Kimberly mentioned, and Matt will go into a little bit more detail on those here in a little bit. Some of the benefit of the water source system is that the ground temperatures don't fluctuate like the outdoor air temperatures do. So that's why Credit Human, with the 300-foot deep underground wells, could store heat from the summer that the water source VRF could use to heat the building in the winter, which that's also something that Matt will talk about, how that ground source system helped prevent major piping loss during the snowpocalypse, like Kimberly mentioned. Water source VRF systems can also provide the option of storing condensing units indoors, which we also see at Credit Human, and both options provide optimal energy efficiency and comfort. Another helpful feature of the VRF systems is just the variety of indoor units you can use, whether you're looking for more ducted options or ductless options. That gets used a lot in some of the older buildings that have real high ceilings where you can't pass ductwork through spaces. VRF tends to be a good option for that, being that you can just run the refrigerant piping in a lot smaller area to get it in spaces, and even not even needing ducted options by using some of our cassettes. Contrary to the outdated ideas based upon long discontinued equipment, today's VRF heat pumps are able to provide heating in extreme cold. VRF systems can perform in conditions as low as negative 27.4. My 10 years of experience in the engineering field before this, that seems not realistic, but we have a lot of systems installed in areas that have hit this temperature, and it functions in the negative 27 degree temperatures. Using our hyperheating technology, building owners can ensure that their tenants and occupants are comfortable year-round with or without auxiliary heating. This facilitates opportunities to save money and be more sustainable, as you're not relying on fossil fuel burning systems for extra heat. Although the Credit Human building in San Antonio didn't require the additional heating systems, the fact that it's possible speaks to the capabilities of the VRF systems that they used. So ventilation, that's what that's the first question we get asked on VRF all the time. And proper ventilation is a huge priority. Coupled with VRF zoning technology, airflow is never recirculated from one zone to another. This method of operation enhances indoor air quality. By using ERVs to recover the waste energy from a building by capturing and repurposing thermal energy from exhaust air, you can move the building's exhaust air through a heat exchanger where it meets and tempers a stream of outside ventilation air that the ERV moves into the building from another direction. Through this crossing of streams at the heat exchanger, the ERV recovers about 70% of sensible energy and 60% of latent energy. ERVs are cost-effective in moderate or dry climates. In more humid climates like we have here in the South Texas market, we use dedicated outside air systems quite a bit, and that tends to be a better solution for our climate. The dedicated outside air system can condition up to 100% of the ventilation air load and can offset humidity from the outdoor air. It can also deliver dry air to offset moisture already within the building. With the DOAS, outdoor air enters through one side of a rotating heat exchanger while exhaust passes through the other side when we utilize ERVs. Outdoor air units combine ERV and DOAS capabilities to condition 100% of the ventilation load. They connect directly to a VRF condensing unit like an indoor unit that are purpose-built for zoned ventilation. Outdoor units are useful in facilities with diverse ventilation requirements. We've got a lot of different solutions to employ the variable compressor options to get the best efficiency. And in spaces where you need to do tenant billing, that's another option that VRF makes it easy to do. The inverter compressors, they only use the exact amount of energy needed to reach a zone set point. That said, it's a huge benefit for all types of buildings with tenants. If a building owner bills individual tenants for energy consumption or needs to bill for excessive usage, energy allocation controls can be applied to VRF systems, which are a huge advantage. This solves the challenge of energy consumption billing for multiple tenants. They can also be customized to suit a building's individual needs. For example, using our Building Connect Plus, which is a cloud-based control offering, that helps you get the most out of your VRF systems. This feature is ideal for these mixed-use projects as different spaces may have vastly different heating and cooling needs, resulting in varied energy usage. So now I'm going to turn it over to Matt to give us some more detailed stuff about the Credit Human project.
All right, how is everybody? Hopefully everybody's having a good day. So we're going to delve a little farther into the VRF system at Credit Human specifically. So equipment was used and how this VRF system contributed to meeting those ambitious goals that Kimberly mentioned earlier. So if you look at the screen here, we've got I just kind of wanted to show an example of the Credit Human building's operating conditions. So this is kind of a look at this whole water source system and kind of how it was operating on an ordinary day in January of this year. So if you look at the green lines on the slide, those are the above ground condenser water loop through the building and then out to the cooling towers. And those are separated by a big plate frame heat exchanger. And then the gray lines sort of at the top of this little pad, like a little gray concrete pad, that represents the geothermal loop that runs underground. And there's also a plate frame heat exchanger in between the geothermal loop underground and then how we connect to this green condenser, building condenser water loop. So both loops have got a heat exchanger that they utilize. So there's numerous reasons why a water source VRF system was chosen for the Credit Human building. First, of course, was the efficiency and sustainability element. Ground loop systems supply a relatively, constant water temperature, like Kimberly had mentioned earlier, allowing the mechanical systems to operate with optimized efficiency. These systems are especially advantageous in locales like San Antonio, although underutilized until now. San Antonio's got an average outdoor temperatures that fluctuate by almost 90 degrees between summer and winter. While winters tend to be mild, the region's hot and humid summers force air-sourced mechanical systems to work harder to reach a building's indoor temperature set point. So by comparison, groundwater temperatures fluctuate a much narrower range, maybe 10 to 20 degrees Fahrenheit. So ultimately, water source systems used in these climates are able to deliver efficiencies 3 to 4 times higher than an air-sourced VRF system. It's important to note that in this area of the country, water is a big deal if you don't know, because it never rains. So, credit human HVAC specifics. So this project used a total of 41 water source condensing units, all of which are actually housed in the mechanical rooms on each floor of the building. The units are stacked on top of each other on some of the floors where we have more than just 4 units. The indoor installation protects them from the elements and maximizes the building's usable outdoor space. So the interior of the building is served by a VRF system. The majority of the units are exposed. You can kind of see that in some of the pictures in earlier slides and this picture. There's a couple of ductless wall-mounted units, like in back of house areas, but most of it are these ceiling-hung fan coil units that you can kind of see at the middle of this slide with the black refrigerant pipes running to it there above this desk. So as Jamie touched on, one of the great benefits of the VRF technology is the option for zoned comfort control. So each zone is able to have its own set point based on occupancy, usage, or personal preference. In the credit human office space, the system is controlled through a singular interface, but thermostats can be found throughout the space about every 20 feet apart, giving employees some autonomy over their comfort. So you can adjust these individual zones, even though it's an open office space. Some of these zones can still have some local control, depending. There's always someone at one end of the building that's hot and someone else at the other end of the building that's cold. So when it comes to controls, the credit human building has a comprehensive controls network made of local remote controllers, centralized controllers, and expansion controllers. Finally, for ventilation, the building uses some energy recovery ventilators, or ERVs, that are inside the dedicated outside air units on the roof, along with linear expansion valves, or LEV kits, that came from Mitsubishi. And these are tied in with the Mitsubishi condensing units that are the same units that serve all the VRF systems on the floors. So they use the same condensing unit to serve the refrigerant coils in these dedicated outside air units that are on the roof. So next, we're going to talk a little bit more about how this control system integrates with the rest of the building systems. So the credit human building is incredibly well integrated. It's actually one of the most tightly controlled buildings in Texas. This is thanks to, obviously, the robust control system that we talked about on the previous slide, and how they integrate with the building's other systems, including the ventilation, lighting, security, and a host of other items in the building. So what we see here is an example of one of the DOAS units that's on the roof, because this credit human tower has 2 of these DOAS units, a total of 30,000 CFM, 15,000 each, fresh air coming into the building. Anyway, and it's conditions that we captured on an ordinary day last month. So you can see that there's, exhaust air coming out of the building. You can see where you've got air exhausting from the building, coming out of the unit. The energy recovery wheel in the middle that says RHX operation level at 0%. Well, the energy recovery wheel wasn't running that day because it just wasn't hot enough to be able to transfer any of that, cool air from the building to outside. So once it gets hotter, like probably even on a day like today when it gets up to 80 degrees, that wheel will start running and having some of that heat transfer to pre-treat that outside air that's coming into the building. So the photovoltaic system or solar panels that are on the roof, this solar array is actually the largest of any mid-rise or higher building in North America. The 2,638 panels produce about 40% of the building's energy. So combined, the solar array, the VRF system, and other efficient building systems have led to a 56% reduction in energy demand compared to similarly sized buildings with code minimum equipment and envelopes. The choices to use these systems is estimated to save Credit Human 1.45 million kilowatts of electricity a year. In fact, on a square foot basis, the building's utility bill and carbon emissions are reduced by 100% compared to the former Credit Human headquarters that Kimberly talked about earlier. And that really shows when she, detailed what those utility bills cost on that old facility versus this facility. It's pretty incredible that they're actually generating or spending rather what they were spending on energy in the 70s from that original building. So in terms of water conservation, the Credit Human building boasts some impressive numbers there as well. At least 80% of the building surfaces are capturing either rain or solar, normally both at the same time. With that, the building reclaims about 97% of rainwater, resulting in 2 million gallons of potable water saved per year. Compared to the former headquarters, water usage is reduced by about 85% on a square foot basis. Next, we'll take a look at the building's energy use intensity, or EUI. That's the energy used per square foot per year. The lower the intensity score, the better. The infographic you're looking at shows that based on energy data from February 2021 to January 2022, the 100,016 square foot Credit Human building had an EUI of 13.8. So for comparison's sake, the median for similarly sized buildings is 63. Most code-built buildings fall somewhere between the upper 50s and mid-70s. However, the new Building Institute has recently set new targets for medium-sized mixed-use buildings smaller than Credit Human as part of their net zero initiatives. They want to see a median of closer to 25 EUIs or lower. The Credit Human building is a testament to what's possible. Its outstanding efficiency and energy conservation has earned it a number of awards, including the Building San Antonio's Best Green Project 2021, Building San Antonio's Best Large Office Development, the U.S. DOE, the Building Envelope Campaign's Novel 40 Award, and the Texas Rain Charter Award, Texas Rain Catcher Award, sorry. So as the awards and accolades are great recognition for the completed project's performance, but there's also a lot to be said about the process that led to this completion. Or a lot of credit for the Credit Human building stands as such an impressive playbook of sustainability today goes to the way that the team collaborated during the build. From the project's initial framing, the owners were hands-on and felt very strongly that collaboration would be critical to the outcome. So any pre-existing hierarchy was deconstructed early on, allowing every member of the project team to have an equal input and access to information. This took away any finger pointing and instead asked for everyone's input to address problems as they were happening. Collaboration and proactive communication amongst the project team were integral to Credit Human's success and are for any project that hopes to follow suit. One thing that the CEO of Credit Human took very serious was to try to create not just a team atmosphere, but really a partnering between the construction teams, the design team, the equipment reps that were involved. That's why Mitsubishi was involved from day one, where normally the equipment reps look at the drawings, maybe sell the equipment, help out with a few problems here or there, and that's sort of the involvement on a typical job. This case, everyone was in 100% for 100% of the project. And we all had to kind of throw out the old way of doing things and building buildings to try to build this project differently, because we had such steep goals to try to meet. That was really the only way that we were going to be able to get there, and I think it made a huge difference in the success of the project. So takeaways, I think Kimberly's going to take over on these.
Thanks,
Appreciate
Matt.
Everyone.
Yeah. Thank you.
Go ahead, Kimberly.
So we're going to bring it home now. And just the main takeaways, it's hard to actually follow Matt's summary of what was really at the core of the success of the project. But we just want to leave you with, with the idea that really highly sustainable, resilient buildings, they are attainable. We're not trying to sugarcoat it in that the project was hard, it was long, it was hard. And it was really due to people who often don't get recognition, who are often mostly in the field, that brought this project across the finish line. And in that spirit, I want to acknowledge our teammate, Jamie's and my teammate, Chris Vandegrift, who was absolutely key in getting some of our problem systems that were not functioning as designed operational and optimized. So hats off to Chris. So where systems, where we have an intentional goal, starting with ownership, where systems are intentionally designed, constructed, and commissioned, and operated, it's possible to reach these really high resiliency and sustainability goals. VRF systems, in particular ground source systems, have a particular resiliency to very extreme weather conditions, and we've already reaped the benefit from that. The high efficiency distributed air handlers, which allow for increased and continuous filtration, supports higher indoor air quality, and the highly efficient ventilation systems do the same. So with that, I just want to check in again with Jamie and with Matt to see if they have any closing comments that they'd like to leave you with before we open up the floor for Q&A.
Let me just add just a few in there. I mean, kind of like what Matt was talking about, just how the project team really did it. It really did change. It took very minimal effort to really make this a success. It just took effort. And that's one thing that started with the ownership, like he said, all the way down to everyone that's actually turning the screws and hammering the nails. Everyone was involved. No finger pointing happened. It went real smooth. I mean, this project started when I started here. We had just closed the deal kind of that we were going to be the VRF manufacturer then, and I've been with Mitsubishi for 5 years now. So it was a long project, but really neat to see it come along and just showing that these high-performing buildings, they make sense. It makes financial sense. That's one thing. I've been on some of the tour. We did obviously done a ton of tours where we brought people in, and Steve Hennigan, the CEO of Credit Human, is just our best salesman ever. He's like, the stuff just works and it makes sense. And like the 100%, number. That was new news to us. We just heard about that recently from Steve. So that's amazing that we can get to that. That some stuff cost a little bit more on the front end, but was definitely worth it for the life of this building. So, now, if you have anything else you can add.
Yeah, this is Matt. I do just want to say one thing about the mentality of trying to design this building. What Credit Human pushed the design team and us from the construction team to do was to stop thinking about what's typical, what's normal, what normally makes sense. Let's push the envelope of what is possible, and then we'll figure out how to build it. And so he really took everybody out of the normal mindset and pushed the team to think about what is physically possible, and then we'll figure out how to build it. And if we have to dial a piece back here or there because it's not buildable, well, then we'll cross that bridge when we get there. But it was interesting to hear an owner say, I don't want to just build something that works or something that's typical. I want to build something. I want to figure out what is humanly possible, and then we'll go try to build that. So I just wanted to throw that in there.
That's great. Thanks, Matt. So I think we've got 5 minutes left for Q&A. I'm going to hand the floor over to Andy Solage with LMO. Andy, sorry we shortened your Q&A time, but I think it was worth
No
it.
problem at all. Yeah, I think so. So thank you, Kimberly. Thank you, Jamie. Thank you, Matt. And thank you for everyone who just submitted questions reflecting varying levels of familiarity with the VRF product. Okay, so let's jump right into it. So what is the typical life cycle of a water-sourced VRF system in a geothermal installation, and what kind of maintenance is required?
Jamie, you want to take the lifespan question?
Yeah, okay.
I think ASHRAE, what I've seen in ASHRAE, I think what they say is it's about a 20-year life cycle is what they, whenever we're doing energy models and stuff like that for. But I mean, the maintenance for it is key to prolonging anything. But as far as the rest of that question, you can probably handle that one, Matt.
Yeah, I mean, the maintenance side of it is making sure you're maintaining proper water quality as far as this like closed loop condenser water system that runs through the building and through this unit. And that's really a pretty standard condenser water maintenance program. You know, those condensing units don't really have a whole lot of moving parts that you change out. Definitely on the fan coil unit side, you want to make sure you're doing, this is just with every unit, air conditioning unit, changing out filters often, like you're supposed to. But really just keeping up with the water treatment and keeping up with filter changes, I would say, is the main thing to do with this type of system.
So just to be a little more specific, so if we're not talking about the well portion of the system, and we're just talking about the water to refrigerant portion of the water source system, you're looking at a similar life expectancy to the air source system. So 15 to 20 years it on average is what we expect to get out of those portions of the heat exchangers. So 15 to 20 years, a lot of times we see them operating longer than that.
All right, great. Next question. Did the Credit Human project qualify for the U.S. DOE Enhanced Geothermal Systems Funding Program to offset costs? And if so, could you describe the process? And if not, what other incentive programs were used?
I'm not sure if that particular one was used. I didn't recognize the name unless you know, Kimberly.
Yeah, I would say definitely not. That was not. We did not participate in that program. But Matt, do you want to speak to any of the others?
Well, we use some local stuff, like, for example, CPS has some, stuff for using photovoltaic or the solar panel systems on the roof. I don't recall utilizing anything for the water source system. I believe we did get some kind of relief or tax grants for the rainwater capture system. But I don't know specifically if we used anything for the water source or the geothermal system that's in the building associated with this VRF.
Okay. This is a basic question, but a few people have asked it, so I'm going to ask it. Is there an option to integrate VRF with building automation systems or BMSs?
Yes, yeah, and as a matter of fact,
I'll just scroll back to that screen.
Yeah, this system is tied in with the main BMS system. So actually, this screen that you're looking at here is from the BMS system, or what we call the DDC, the system. So the whole VRF system is tied into Trane. Actually, has the control system set up on this building for the BMS. So everything is in that BMS system, the lighting controls, all of our VRF systems, the DOAS unit, which you're showing here, the whole condenser water loop system and the geothermal loop system. We can see all of those pumps and units and everything. This little controller that's on here is a controller that's dedicated just for the VRF system. That guy is integrated into the BMS system so that we can see all of the units on this specific controller. So yes, it is, and it can be, and it is on this credit human building.
All right, great. So was there any concern for freezing pipes in the water source system during the snowpocalypse?
Yes, and we had some pipes freeze outside that were going to the cooling towers. So after that happened, we replaced those, and because they weren't insulated, and I believe they insulated some of those lines. It was a lot of the plastic stuff that was running underneath the cooling towers. So yeah, we definitely had some stuff freeze when it was 7 degrees. But they changed they added some insulation. They changed a little bit of the operation to flow more water. Have the pumps run a little harder when it does freeze, so that there's more water running to keep things from freezing in the future.
All right, and so I'm going to ask, I think, 2 more questions, and then we'll close out. So so can you discuss the differences between an air source system and a water source system in this particular environment in San Antonio? Is there an advantage to using water source versus air source?
You want to take that, Jamie?
Yeah, I can take that one. Most stuff we do in the South Texas area tends to be air source. You really have to look at the ground conditions to see if water source makes sense in your locations. Most of the stuff around here in San Antonio, it doesn't make sense to do the full system on it. Like the water source or the geothermal part of this one is just kind of knocking the peaks off. It's not handling the whole load of the building, except for in kind of some of the shoulder seasons it can. But most of our systems are air source that we do here in San Antonio, or really Austin, South Texas, are mostly air source. And it's the nice thing on the water source is, like you've seen in some of the pictures and stuff, it's the condensers and everything are inside, easy to maintain. There really is kind of minimal maintenance other than the water conditions, but which once you get the condenser water system set up, it's closed loop. So just kind of keeping that out of trouble. The air source is really, the maintenance on air source is very simple, really just cleaning the coils with water, just some basic stuff like that. But and like I said, we have some of those where even our air source systems have the condensers mounted indoors, which that's what they do a lot in the Northeast where they're doing high-rise stuff. They will have the air source condensers in the middle of a building with it rejecting air through some louvers through the side of the building. We have a few facilities here in the San Antonio area, up in the Cibolo area. It's a medical office building where all the condensers are in the basement of that of the medical office building. So flexible, and maintenance is minimal compared to other traditional systems.
All right. Okay, so last question. So did you run the energy calculation, and what type did you run? Was it budget or prescriptive, or the prescriptive method for the Credit Human project?
I don't know if I know what is meant by the budget method. The load calculation
definitely wasn't the budget method, because this. Well, let me go ahead, Kimberly, because I'm not sure if I can answer the question either.
The load calculation, I think, was performed in Energy Plus. It might have been a DO2 energy model, and there was a lot of work that was done at that design phase, because like Matt pointed out, like there's a lot of business as usual that happens, especially in design phase, where you've got MEPs that need to be careful about their time on the front end. They don't even know if they're going to get a project yet, or they don't know if they're going to get beyond the design phase of the project. And so there's a lot of, cutting and pasting and business as usual and default inputs and all that go into your energy model. So that's somewhere where we broke it down, and we really took some time to look at the actual proposed building construction type, the occupancy, the ventilation rates, all of that stuff. So we took extra time on that. And then in terms of calculating the ROI, which maybe is where this question is starting, like how did you get those ROIs? The owner did their own financial analysis, and they did a much more holistic analysis than what is usually considered in like a quick payback kind of calculation. So they were looking at the cost of water, the cost of electricity, other maintenance and operations costs beyond just electricity and water. And that's how they came up with that 12 to 13 year ROI, which again looks like they're gonna do better than that probably.
Just kind of expound on that a little bit. Yes, he did. And one thing he said, like in some of the keynotes that I attended that he gave, was that you cannot use a simple payback method on any of this stuff. It's, obviously the best person to do that analysis is the guy that owns the bank, to do all the math on that to see what it truly costs him, and that's what he really did. The VRF system can save money in other spots other than just energy. It's going to save money on your electrical feeder sizes coming in. I mean, it kind of compounds on stuff. You can't just look at it as, the MEP number was this, or the mechanical equipment number was this compared to a VAV rooftop. I mean, you can't look at it like that, because one of them may have electric heat. We don't have any electric heat on ours, so there could be huge electrical savings in comparable systems for the same building.
But there was a question that snuck in after our last question, but I think we should answer it. Just indulge me for one moment. So with New York and other states moving away from fossil fuels, is Mitsubishi Electric working on lower temperature heat pumps since we see negative 20 degrees or lower?
Yes. Yes, we are. We rate our cold climate heat pump systems. One of the rating metrics we use is, can it deliver 100% capacity at a given temperature? And so we started off by with 5 degrees Fahrenheit, we could maintain 100% capacity. Now we have systems that are being rated at being able to deliver 100% capacity of the rated capacity down to negative 10, and we keep on pushing that boundary. And when the numbers we publish as a manufacturer, they're conservative, and so we have systems that have been, with every winter blast that happens up in the central U.S. And Northeast, we get more reports of, systems operating at negative 12 and the like, and pushing out 120, 115 degree air. So the cold climate heat pumps, yes, continue to evolve and be developed to be a sole source of heat, even in very extreme cold temperatures. That's not to say that we don't support, backup heat and emergency heat, especially in those types of extreme cold climates. But the systems, yes, are being designed and evolved to be a sole source of heat in very cold climates.
Perfect. Thank you. That was the last one.
Okay. Well, thank you, Andy. Thanks to our attendees. We appreciate that you stayed with us an extra 10 minutes. We hope you got some useful information about this project. Really, we're hoping to inspire designers, owners, architects, GCs to, like Matt was talking about, think outside the box and to envision what's possible. There are resources out there to make sustainable and resilient attainable. So we're hoping you go for it. And we have some additional resources here on our website, our case studies. Also, what's not listed here is 1703broadway.com. It has some more information about this project in particular. Thank you so much to my teammates, Jamie Armstrong and Matt Dunn, and thanks to LMO for facilitating this and ASHRAE for hosting us.